Salutations, Seahawks. Welcome to your second lesson of Module 6. It's going to be a great one. Today, we're looking at 6.1b, the rational number system. We're going to practice rewriting repeating decimals as fractions. Since we already know repeating decimals, like 0.3 repeating, can be written as 1/3, we are going to look into exploring other repeating decimals, any repeating decimal in the whole world, and you can write it as a fraction. So we're going to review the real number system, and hopefully you already watched that quick video about reviewing the number system. We looked at it in Module 1, and we've been looking at the real number system throughout the whole year, thinking about natural numbers, whole numbers, integers, rationals, irrationals coming soon. So be able to use an equation to rewrite any repeating decimal as a fraction in simplest form. And we're going to see a pattern if all the digits repeat to the right of the decimal point, so we can use that, a slick trick. And we're going to use these values, like those fractions, to add, subtract, multiply, and divide other rational numbers. So it's going to be super fun. Okay, so 6.1b lesson. First things first, let's review what these different number sets are. So we are going to define them. We'll start with the natural numbers and the whole numbers. So the natural numbers, so I can make this a little bit clearer for you. Awesome, that looks better. So the natural numbers are the counting numbers. It's the first set of numbers used to count items, and the smallest natural number is 1. So in the natural number set, it goes 1, 2, 3, 4, and then off and off and off. You might say the biggest number is infinity, but infinity is not a number, you guys. It's just a symbol. It's just an idea, the biggest number. So we could say, like back in the day, natural numbers, we can count like how many pumpkins someone has, or how many loaves of bread, or how many chickens, right? If we were going to trade, I'm going to be trading some eggs for your pumpkins that you grew, right? How many eggs? I'm not going to trade you half an egg. Like, that's not cool. And you're not going to trade me half a pumpkin, right? So then we have the whole number. So we had to have a number to represent when people have nothing. What does it mean when you have nothing? It means you have 0. So we have the whole numbers, and the whole numbers, it's a whole. Get it? Like, what does a whole look like? It looks like the number 0. So all the natural numbers and 0, and the smallest whole number is 0. So the set starts at 0, and then it goes 1, 2, 3, and so on and so forth. Then after the whole numbers, we have the integers. The integers are all the whole numbers and their opposites. So this is the first thing we come into negative numbers. So there's no known smallest integer because we can always subtract 1 to get to the next one. So notice I have an ellipse here, meaning it's starting over in negative infinity, right? And then it's going to continue -3, -2, -1, 0, 1, 2, 3, and then there's another ellipse. It's going to continue over to positive infinity. Rational numbers, so this is where the good stuff happens. And the rational numbers are any number that can be represented as the quotient, fancy word for division, of two integers, p over q, where q can't be 0. Like, wait, Ms. Barr, why can't q be 0? That's because we can't divide by 0. Never give up, never surrender, and never divide by 0. You can't do it, it's undefined. So this includes all terminating decimals like 0.32, 32 hundredths, right? 0.25, 1/4. So terminating means the decimal ends. Like, that's it. That's all she wrote. And then repeating decimals like 0.3 repeating with a bar over it. And of course, square roots of perfect squares, because that's what we've been exploring this module. So what I'd like you to do is I'd like you to take all these numbers and I'd like you to sort them into the sets, and some will be used more than once. And if a number does not fit into the category, I'd love you to circle the number. For example, if I look at the number 45, I know you're like, Mrs. Barr, why'd you do such an easy one? Because you guys can do this. Oops, I'm not going to circle it because you circle it if you don't use it. So 45 is natural. It's also a whole number. It's also an integer, and it's also rational, like 45 over 1. So maybe I'll like cross it out if I use it. But remember, if there's a number you don't use because it's not natural, it's not whole, it's not an integer, it's not rational, it might be irrational. that's when you circle it. Okay, go ahead and pause the video, and I'd like you to finish sorting and then take a look at number 1 below. Okay, let's see how we did. Okay, what numbers did you put as natural numbers? That's right, 45 square root of 121, which is 11, and square root of 16, which is 4. The whole numbers are all the natural numbers, 45 square root of 121 and square root of 16 plus 0. The integers, we're going to have all those whole numbers, so 45, 0, square root of 121, and square root of 16, plus their opposites, so -8 and negative square root of 81, which is just -9. And the rational numbers, we're going to include all the natural numbers, all the whole numbers, and all the integers. And then I'm going to add any of the repeating decimals, so decimals that have a bar over them. The fractions, so 1/3, 1 4/5, square root 1.96 and square root of 0.25. 1.96 and 0.25, those are multiples of perfect squares. And then these are terminating decimals, 0.25 or 3.14. Okay, so what numbers did we not use? We didn't use pi. We didn't use 1.732050, blah, 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 blah. Not sure. It just keeps going. Square root of 99, 3.46213, dot, 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 dot. Square root of 15 and square root of 2. So these are numbers we did not use. So taking a look, what observations can we make? We can say those are irrational numbers. So they are decimals that never end and never repeats. It includes square roots of non-perfect numbers, or multiples of them. And it's non-terminating and non-repeating decimals. So we cannot write these as a fraction. Can not be written as ratios. Because remember, rational numbers, I like to call them rationals because it has the word ratio in them. We can write it as a fraction. But these are irrationals. Nice work, mini mathematicians. Okay, so what we're going to do is we are going to keep going, and to start off, well, let's define irrational numbers one more time, just to make sure we really know what it is. So irrational numbers can not be written as fractions, also known as ratios. And they are decimals or symbols that represent decimals, such as pi or the letter E. Interesting. Decimals that never terminate, meaning they never end, and are non-repeating. So some students may think, oh, but repeating, like if I had 1.12, 112, 1112, 1112, like it's kind of like there's a pattern, but pattern and repeating are very different things. So by repeating, if we had something like 1.121212, I could put a bar over it because that 1, 2 goes on forever. I can't put a bar over this. So this would be irrational, but this would be rational. Nice job. Okay, so taking a look, what I'd like you to do is I would like you to finish 3 and 4, and then we'll get into some fun converting in just a moment. Okay, what did you circle on number 3? You are correct if you circled two of them, irrational numbers, square root of 20 and 0.50899173. This is a rational number. It's a repeating decimal. This is a natural number, a whole number, a rational, and an integer because it equals 8. This is a terminating decimal, so we know it's rational. And this is a repeating decimal. Sometimes that's how I'm going to trick you into thinking it's not terminating and not repeating because there's just no bar over it. Look at what the numbers are, you guys. Just don't look for bar. I know it's great to look for bar. Okay, so taking a look, how do you know if a decimal is rational or irrational? Well, if I look at a rational number, I know that the decimal terminates. Because it's talking just about decimal numbers. So the decimal terminates, meaning it ends. The terminator, right? He ends things. Get to the chopper. Not very good impression, sorry. Or it's an or situation. So maybe the decimal terminates, or this happens, or it repeats. So maybe you have a bar 1R. Okay. This is an or situation. Like if we went and got ice cream, you could have chocolate or vanilla, but you can't have both, right? It's an or situation. However, if you have an irrational decimal, you know that it's non-terminating, meaning it's not ending. ING. Sorry about that, you guys. And this is an and situation. We need both of these, right? We want them both, non-terminating and non-repeating. Maybe you have a ... at the end. Okay, so because we know that all rational numbers, terminating decimals or repeating decimals, can be written as a ratio because they're rational, we're going to do that. We are going to convert repeating decimals into fractions and terminating decimals into fractions. And you guys already know a lot about terminating decimals, writing them as fractions, because you know so much about decimal places. For example, if you got something weird like 32 hundredths, well, you know that's 32 hundredths, and then you could just simplify, like divide by 2. What do you got? Like 16 50ths, divide by 2 again. I guess I could have done 4 from the beginning, and you get 8 25ths, right? So, and you know a lot of other ones, like you already know 25 hundredths is a quarter, 1/4. And you probably also know what 1/3 is equal to, right? Yeah, it's 0.3 repeating. So you know a lot of these, and we're just going to work with some of the trickier ones. Okay, so some of the trickier ones. Convert the decimal 0.5 repeating into a fraction. So this is how we do this. First thing we're going to do is we are going to set our repeating decimal equal to a variable. I like to use a. So let a equal 0.5 repeating. Now what we're going to do is we are going to chop off the repeating part because that's what we don't like. And when we don't like something, we chop it off. So let's take a look. So if we have a is equal to 0.5 repeating, well, I notice that 0.5 repeating part, since I have an equation where both sides are equal to each other, I can multiply both sides by 10. Equality property of multiplication. From here, I have 10a is equal to 5.5 repeating. Because remember, this 0.5, it just went on forever. So when I multiply by 10 and move the decimal over once, now it's 5.5 repeating. Okay, well, remember what I said. I wanted to chop off the repeating part. Well, that is 0.5 repeating. Notice it's also equal to a. So I'm going to subtract the same amount from both sides, but it's going to look different because I want this as a like term. So I'm going to subtract a from this side to get 9a. But you need to subtract the same amount from both sides. But remember, a is equal to 0.5 repeating. Line up your decimal point. Can't stress this more because they're going to get harder. line up your decimal point, 0.5 repeating, and we're subtracting. And oh my golly, look at that. The repeating decimal part cancels out, and we're left with 5. But remember, we are still solving for a, because a is equal to 0.5 repeating, and I want to know what 0.5 repeating is as a fraction. Well, a is being multiplied by 9, so let's divide both sides by 9, and we get a to equal 5/9. Ah, very nice. So that tells me that 0.5 repeating is also equal to 5/9. And that's your final answer. So let's practice that. We're going to practice that for 0.74 repeating, 2.4 repeating, and 1.05 repeating. Okay, so first thing I'm going to do is, again, set the value equal to a. So let a equal 0.74 repeating. Okay, next thing's next. If we multiplied both sides by 10 here, we would have 10a equal to, move the decimal over once, and if you like to add some more 7/4s here, be my guest. 7.47474, right? Because it's 7/4 repeating. However, if we go to subtract a now, 0.74, notice they're not going to line up, you guys. None of the repeating stuff. It doesn't go away. It's still going to be repeating. So that means we're not going to be multiplying by 10. Bum, bum, bum. Exactly. So maybe grab another piece of paper, or you can fit it right here. I have to write a little bit bigger so you can see. So I'm going to grab another piece of paper. I'm just going to label it 6a, 0.74 repeating. So I'm going to let a equal to 0.74 repeating. And, oops, forgot my let a equal that. So now if a is equal to 0.74 repeating, I know I can't multiply by 10. So we are in the decimal system, so every decimal place is a base 10. Notice if we moved over to the end of our repeating decimal, we need to move over 2 decimal places. So I'm going to multiply both sides by 100. Ooh, by 100. That'll be nice. I'm just going to add this 7.4 here for my brain to figure it out a little bit better. So now I have 100 A's is equal to 74.74 repeating. Oh, okay, I think this is going to work better. So again, subtract 1A from both sides. But A is equal to 0. Line up your decimal place. 7.4 repeating. And we're subtracting. Yay! The repeating part is just chopped off. So from here, we get 99 A's. Got 99 A's is equal to 74. Okay, so from here, again, we want to get A by itself. So we're going to divide both sides by 99, and A is equal to 74 over 99. Double check, see if you can simplify. I cannot. So that means I know that 0.74 repeating is equal to 74 over 99. Okay, so equals to 74 over 99. And I'm just going to write C work at end with a happy face, because it's kind of like a please and thank you. How are you supposed to get what you want if you don't ask nicely? Okay, let's take a look at 6b. So when we're dealing with a number that's like 2.4 repeating, what's happy here is, what's really nice is you can always think about this as 2 plus 0.4 repeating. Sometimes a little bit nicer to convert 0.4 repeating first and then add the 2 at the end. Okay, and when I look at C, just to let you know, When I look at C, notice we're have 3 digits repeating, so you might want to think about what you need to multiply to get to the end of the repeating decimal. Okay, go ahead and pause the video real quick, and then we'll go over it as soon as you're ready. Okay, let's take a look. So when you let A equal to 0.4 repeating to then remember to add 2 at the end, I'm going to multiply both sides by 10 since there's only one decimal place that's being repeated. And when we get 10A is equal to 4.4 repeating, so when we subtract A, or in this case 0.4 repeating from both sides, we get 9A is equal to 4. We divide both sides by 9 here, and we get A is equal to 4/9, which tells us we have to add 2. 2 and 4/9 is equal to 2.4 repeating. But notice we wanted this just as a fraction. So 2 and 4/9, 2 times 9 is 18 plus 4, 19, 20, 21, 22. So this is 22/9. Give it a circle for my answer. Okay, really nice job. When you take a look at 105 repeating, so 105 thousandths repeating, of course since I have all this room, let's use it. We let A equal to 0.105 repeating. So if we have A equal to 0.105 repeating, notice all the decimal points are repeating to the right of the decimal point. And I'm going to multiply each side by 1,000 because we have 3 digits being repeated. So here I'll have 1,000A is equal to, move the decimal over 3 times, 105.105 repeating. Subtract A from both sides. Remember, A is equal to 0.105 repeating. Line up your decimal place. So I have 999 A's equal to 105. Of course, I would want to divide both sides by 999. A is equal to 105 divided by 999. And notice I'm thinking 3 goes into both of these because 5 plus 1 is 6. So I'm going to just 105 divided by 3. I get 35. And 999 divided by 3. I get 333. I'm pretty sure that's as far as I can go because 5 plus 3 is 8, and 3 doesn't go into 8. So I just used the 3 trick, and we've talked about that a couple times this year. If you have a number like 105 and you add up all the digits, if that sum is divisible by 3, the whole value is divisible by 3. Okay, so awesome. Oops, I forgot my final answer. So remember that 0.105 repeating is equal to 35 over 333. Okay, so let's take a look at the next one. It says, fill in the table with the information we found above. Is there a pattern that develops when converting a repeating decimal into a fraction? Oh, let's look for this pattern. Okay, so 0.5, and this is going to be, when we put this fraction in, we're going to put in unsimplified form. Because we really want to look for this pattern. That's going to be the way we see it the easiest. So 0.5 repeating, 5 over 9. 74 repeating, 74 over 99. 2.4, well, 2 and 4/9. 105 over 999. Miss Barr, how did you do that so fast? Well, even if I had like 0.8 repeating, that's going to be 8/9. If I had 0.13 repeating, 13 over 99. 0.128 all repeating, 128 over 999. Ooh, do you see the pattern yet? I hope you do. So is there a pattern? Yes. When all the digits to the right of the decimal point are repeating. Meaning they have that bar over them, or you notice they're always all repeating. The fraction has a denominator of 9s equal to the number of digits being repeated and so look, 1 digit repeating, 1 9 in the denominator. 2 digits repeating, 2 9s in the denominator. 1 digit repeating, 1 9 in the denominator. 3 digits repeating, 3 9s in the denominator. And the numerator is the repeating digits. But like one set, right? It's the digits being repeated. Cool. Do you like our new slick trick? I mean, we're not going to have to do all of this ever again. Only if all the digits are being repeated will we not have to do that again. But we're going to have to do it again because they're not always all going to be repeated. Yay! Don't hate me. Okay, so this pattern that we described in number 7, does this apply to 0.1 with just the 6 being repeated? No, it doesn't. No, sad face. But happy because we get to do more math? No, not all the digits are being repeated after the decimal point. So that 1, you guys, ruins everything, right? Ruins everything. Okay, but it's fine. So we're going to use, though, the same method to convert. So we're going to write an equation. We're going to set it equal to A. We're going to multiply by 10, 100, or 1,000, and we're going to solve. What's really important here is we have to remember we cannot leave decimals inside a fraction. For example, if you had like 1.2 over 9, you can't leave it like this. We don't put decimals in fractions. We don't put fractions in fractions. And I don't know how you put a fraction in a decimal, but you can't do that either. It's not simplified all the way. So here, easy way out, you can always just multiply by 10 to move the decimal over, and then you'd have 12 over 90. And then, of course, you'd want to simplify by dividing by 2 and get 6 over 45. Oops, and then you can divide by 3, right? And get 2 over 15 would be your final answer. Okay, so remember, those are some things you can do. There could be other numbers I could have multiplied here by first. I could have probably multiplied by like 5 or something to get closer at first, but can't leave decimals in a fraction. Okay, so convert the repeating decimal 0.1 with just the 6 repeating into a fraction. So good old let statement, let A equal the repeating decimal we're looking at. Okay, so now that we have A is equal to 0.1 with the 6 repeating, remember we want our repeating decimal to line up. If we go to the end of our repeating decimal and go back 1, notice we have 1 decimal place, so we're going to multiply both sides by 10. When we do that, we have 10A is equal to, remember this is a 6 being repeated. When we multiply by 10, we're going to end up with 1.6 being repeated. We're going to subtract A from both sides. This is where lining up your decimal point is really important and filling in any numbers. I know typically when we're subtracting and we think about filling in numbers, we think of 0. We can't think that way anymore because some of these repeating decimals, it's not a repeating 0, right? Okay, so we're subtracting A. Remember, A is 0.16 repeating. Line up your decimal place, line up your numbers. From here, I end up with 9A is equal to, man, the repeating part is chopped off. Mwahaha. And now we just have 6 minus 1, which is 5. So we have 1.5. How cool, the repeating part is gone. But we still need to solve for A. So we're going to come back up here. We have 9A is equal to 1.5. I'm going to divide both sides by 9 to get A by itself. And I get A is equal to 1.5 over 9. You cannot leave decimals in fractions. They are not simplified. So again, you could probably think of a number that gets rid of the decimal and it's easy to simplify from the beginning. But I'm just going to multiply by 10 and just do a little more simplifying. I'll get the job done. Move decimal over once, 15 over 90. I notice 15 goes into both of these. So when I divide numerator and denominator by 15, I get 1 over 6. So from here, we know that 0.16 repeating is equal to 1 over 6. Nice. Okay, so what I'd like you to try is looking at number 10. Again, what I like to do is I like to think about this as 2 plus 0.015. And notice just the 1.5 is being repeated. So I'm going to let A equal to 0.015. You might be like, Mrs. Barr, why do you take the time to write it that way? It's so easy. Because if I didn't write it down, I'm probably going to forget to add 2 at the end, and you do all this beautiful work, and then you get the problem wrong. So sad. Okay, so go ahead and finish number 10, and we'll be right back to go over it. Okay, let's go over it. Did you get 133 over 66? Oh, no? Okay, let's go over the work then. Okay, so again, when I first started multiplying by 10, the repeating part was not canceling out. So you guys, just try again, right? Not a problem. So then when I multiplied by 100 on both sides, yes, the repeating part is canceling out. I got A is equal to 1.5 over 99, which, oh, you guys, you can't leave decimals in fractions. So I multiplied both sides by 10, got 15 over 990, divided it by 15. So I got 1 over 66. You're like, that's what I got. You forgot to add 2 at the end. So then 2 and 166, but since it wants it as a fraction, it didn't say as a mixed number. It said as a fraction. Follow directions. 133 over 66. Multiply 2 times 66, add 1. Yes. Okay. So practicing, we are going to apply our skills to rewrite the decimals as fractions and then do the math. Okay. I will help you get set up. So taking a look, I want you to think about the 9 trick. You can use the 9 trick here and here and here, right? And that's great. It's awesome that we can use the 9 trick. So we can think about, this is 4/10. Oh, I know how to write that as a fraction. 4/10 plus, this is 0.4 repeating, so it's 4/9. Okay, you know when you add, you need a common denominator. So go ahead and finish 11. 12. Well, this is 1.5. Since we're going to be working with fractions, let's rewrite it as 1.5. And this is 0.2 repeating, so it's 2/9. Probably rewrite that as an improper fraction and multiply. Here, you're going to need to do the work to rewrite 0.83 repeating as a fraction. But then when you add it, this is 54 over 99, which we can simplify to be 6/11ths because what goes into both of those? That's right, 9. Okay, 14, you might be like, oh no, I don't want to do that whole equation for both of these. What if I told you you didn't? Would I be your favorite 8th grade math teacher ever? Okay, I hope so. So then let me show you the trick. This is 1.04 repeating. This is 2.05 repeating. Notice the repeatings line up as we line up our decimals. And this is 3.09 with the 9 repeating. So all you have to do is let A equal this or let A equal 0.9, just the 9 repeating, and add it to the 3. Does that seem so much better than doing the process with 2 numbers? Not so bad. Okay, so take a moment, finish 11, 12, 13, 14, and I'll catch you when you're done. Let's see how you did. Okay, number 11, I told you can use that 9 trick. So what did we get? We got 38 over 45. Remember, adding, we need a common denominator. I left this as 4/10. I could have simplified it to be 2/5 and maybe use some smaller numbers and not have to simplify at the end. Oh, hindsight 2020, right? Okay. Remember, no mixed numbers in your answer. We want simplified fractions. So here we change 1.5 to 3/2. We're multiplying by 2/9. Do some cross canceling to get 1/3, or just simplify it at the end to get 1/3. Number 13, our final answer should be 91 over 66. When you rewrote 0.8, which is the 3 repeating, you should have gotten 5/6. So then you're adding 5/6 and 54/99ths, or sorry, 5/6 and 6/11ths. And 66 is your common denominator to get 91 over 66. And number 14, when you rewrote 0.09, which is the 9 repeating, you got 9/90ths, which is about 1/10 plus 3 is 31/10. And I understand 1/10 and 0.09 repeating, kind of rounded, right? But this is our process. This is what we're working with. And I appreciate all your hard work. You're going to have some more practice with this on your homework. And just remember, if you start multiplying by 10 and it doesn't work, try 100. Really think about, how do I make those repeating decimals line up so we can chop them? Thank you so much for your hard work. Stay psyched, do your best, be nice to everyone, and I'll see you next time.